you guys doing? Here we are at the end of chapter 3. Almost. We've got 2 sections left, and we're looking at section 8, which is solving equations and formulas. Our vocabulary today is simply dimensional analysis, and basically what dimensional analysis says is if you have some kind of relating quantity, so we know E equals mc squared, right? Referring to the fact that energy is equal to mass times the speed of light squared. So these are definite quantities that are relating to one another. Dimensional analysis says that gives us the power to take these quantities and rearrange them so that instead of just talking about energy is equal to mass times the quantity of the speed of light squared, right? We could change this around and let's say I wanted to solve for m. So if I wanted to get m by itself, I'd have to get rid of c squared. So I divide both sides by c squared. On this side, they'd cancel out, and I'd get that mass is equal to energy divided by the speed of light squared, right? Kind of cool. So that's what dimensional analysis gives us the power to do, and that's what we're going to be doing. Sometimes you'll see this referred to as literal equations. Sometimes you'll see this referred to as literal equations. And so this is something that you, if you're like searching online and looking for other tutorials about the topic we're going to talk about, it might be under the category of solving literal equations. And dimensional analysis takes on some other concepts. So I'd look here if you needed some extra help. All right, so let's go ahead and take a look at some of the situations we might be involved in. So here's one. We're going to solve for y. So notice we're not solving to get a numerical answer because we have another variable here, specifically x. So I'm going to get a thinner pen. So we're going to try to isolate y. So I take the problem just as I normally would if I were solving any kind of equation. I'd sometimes draw a line right down the center, right along the equal sign. And what I'm going to do is isolate the y term. So the y term, so I want y's on one side and everything else, not just constants, but everything else on the other side of the equation. So I need to get rid of the 3x. I get rid of that by adding the opposite. I'm going to add a negative 3x to both sides. When I do that, minus 4y is by itself, which is a good sign. That's what we want. And then I have 7 minus 3x. The next thing I'm going to do is get rid of that negative 4 by dividing both sides by negative 4. And voila, I have isolated y. I've solved for y. Y is equal to an expression, 7 minus 3x divided by negative 4. One thing we could do to kind of change this around is, and I'm just going to show you equivalent ways of writing this. I can write negative 3x plus 7 over negative 4. Can you see why? Because this is a negative 3x, this is a positive 7, and the negative 4 stays the same. I could also divide everything by that negative 4, so I can write it like this. Now tell me if this makes sense. I have a positive 3x minus 7 over positive 4, right? Why is this the case? Well, in a way, I'm kind of multiplying top and bottom by negative 1. Why is she doing this? This is crazy. And then I rock a distributive property here and here. So what happens is the negative drops off of these guys and this guy gets to be negative instead of the denominator. Sometimes you'll see the textbook write answers in a way that leaves the denominator positive. I just wanted you to see that. All right, so let's take a look at this guy over here. So we're going to solve an equation for a specific variable. Again, we're doing the same thing. We're going to isolate m. Isolating m basically means, oh no, what's the problem here? What do you notice? We've got an m term here and an m term here. So what I need to do is make sure my m terms are on one side of the equation and my other stuff is on the other. So let's get started with that. So I'm going to just put all my m terms on the left side and everything else on the right side. Okay, so with that, something's got to go. This is a minus t. I'm going to get rid of the t. I'm subtracting t, so I'm going to do the opposite and add t to both sides. T is such a horrible one to use because it looks like a plus sign, but whatever. We're tough. So we get 2m is equal to sm, and then over here, we literally have 5 plus t, okay? And now we want the sm on the other side. How do we do that? Well, I've got to move this by doing the opposite. I'm going to add the opposite, which is to subtract sm. And I know already somebody is thinking, this is not going to work. How do you join like terms together when one of the terms is kind of a variable term? And we'll get to that in a minute. On the right side of the equation, we have 5 plus t, and we're just going to sit here and take a moment and breathe. So we gathered all of our m terms to the left side. Everything else is on the right side. Now we need to really kind of see if we can isolate m, because that's our goal. To isolate m, we're going to do something called the reverse distributive property. That's not a real thing. It's really called factoring, but we haven't gotten into it yet. So let's talk about what the reverse distributive property looks like. I know when I'm doing the distributive property, here's a little thought bubble. I'll have like an a on the outside, a b plus c on the inside of parentheses, and I recognize that this is equal to a plus b times a plus a times c. Blah, tongue twister. So these two are equivalent, distributive property. But what happens if I go in the opposite direction? The opposite direction tells me if I've got the same factor in both terms, I can pull it out and then leave both of those terms together. I know somebody's like, I don't know what you're talking about. Over here, this m is the same here and here. The reverse distributive property, soon to be known as factoring, tells me that I can pull that m out and have a 2 minus s left. Stop and breathe. You see it, don't you? M times 2, m times s will give me this. So what I've done is I've pulled the m out. The reason why is because whenever I solve equations, I need to isolate that variable. I got to isolate that m, and that's what we're solving for, right? Don't forget what you were looking for. We're looking to solve for m. So I'm pulling that m out. When I do that, I have 5, wrong color. I have 5 plus t on the right side, and I'm going to divide both sides by 2 minus s. Is that all right? And when I do that, I've got my solved problem, 5 plus t over 2 minus s is the value of m. That one was tricky. I think you might want to watch the video portion of that one twice because it was really a hard one. All right, let's keep it moving. So looking at example 3, we're going to use a formula to solve a problem. Here it goes. Use the information about Kansas City hailstorm at the left, which is not there, but I'll get it there. And the formula for the circumference of a circle is c is equal to 2 pi r, where c represents the circumference and r represents the radius. The first thing we're asked to do is to take this formula, c, circumference is equal to 2 times pi times r. We're actually asked to solve for r. We got to get r by itself. So, you know, I like to highlight what the thing I'm going to solve for. I need to isolate r, so I'm going to leave r's terms on one side and everything else on the other side. So it looks like I'm going to isolate r on the right. Who's bothering r? 2 pi is bothering r. How are they bothering r? By multiplying with r. Opposite of multiplication? Division. So I'm going to divide both sides by 2 pi. That wasn't too bad. So when I solve for r, I see that the radius is equal to the circumference divided by 2 pi. So now let's get some more information so we can answer this question. So let me see if I can find it. Okay, so over here it's showing us that on May 14th in 1898, a severe hailstorm hit Kansas City, and the largest hailstones were 9.5 inches in circumference. Windows were broken in nearly every house in the area. Pretty impressive. So let's remember that information. 9.5 inches was the circumference of those pieces of ice during that hailstorm. So with that in mind, let's see if we can answer this question. It says, find the radius of one of the large hailstones that fell on Kansas City that year. So we remember that the circumference was equal to 9.5 inches, which is pretty huge. So we have up here a formula that will convert the circumference into radius. So let's go ahead and see. So radius is equal to circumference divided by 2 pi. And you guys can see why this is helpful, because if you know that you're looking for the radius, it's nice to have the formula solved for radius. So we've got that the radius is equal to 9.5 divided by 2 times pi. And we would probably plug this in our calculator and get the following answer: approximately 1.5 inches. So this next one, let's see if we can actually get that. This next one, we're going to use dimensional analysis. The formula S is equal to 1/2 AT squared represents the distance S that a free-falling object will fall near a planet on the moon in a given time t. Blah. Okay, so in the formula, A represents the acceleration due to gravity. So we know that S represents distance, A represents the acceleration given gravity, and T represents time. Did they give us time in what? I guess it might be time in seconds. So solve the formula for A. Well, we can do that. We're pretty good at this now. We're getting to be professionals. So we've got A T squared. We know that we're going to solve for A, so I'm going to highlight that. That's my fun thing to do. And I need everything else to go over to the other side. So who's bothering A? 1/2 is bothering A. How's 1/2 bothering A? By multiplying. How do you get rid of a fraction when you multiply? You multiply by the reciprocal. So let's first get rid of the 1/2. By the way, there's more than one way to skin a cat. Like there's more than one way to do these problems, but this is just the way that I like to approach it. So notice that the 2's cancel out. So I'm left with 2s on the left side, and on the right side I have AT squared. A is still not completely isolated. So with 2s equaling AT squared, T squared is bothering A. How do we get rid of T squared? Well, recognizing that T squared is multiplying with A, we need to make sure we divide T squared away. So what I do to one side, I do to the other, and I've got that A is equal to 2s over T squared. Pretty cool. So the next thing we need to do is use this information, this new formula that we created to solve this problem. A free-falling object near the moon drops 20.5 meters in 5 seconds. So we've got distance here, and we have time. What is the value of A for the moon? So we've got distance and time. How can you use that? Pause me and try to start figuring out the problem on your own. Hopefully, if you did pause me, you would see that you would put in for S, the distance, which is 20.5, and then T squared, you're going to put 5 squared, and that's going to give you your A value because we're directly using this formula that we created. So with a little bit of calculator pushing, we would get that we're really doing, up at the top, we'd have 41 divided by 25 over A. We could not use a calculator to do that, I think. So the acceleration would be 41 over 25 meters per second. Let's go ahead and get a numerical value. I will use a calculator. So we get 1.64 meters per second is our acceleration. All right, actually 1.64 meters per second squared. My bad, because our time is squared down there and acceleration is in meters per second squared, and because it's time squared, and we'll talk about that when you get into physics. Okay, so that's it for us. Let me know if there are any questions. I look forward to talking to you, seeing you, working with you, and you know that you need to talk to me and call me and let me know what's going on so I can help you out. Take it easy, guys. Look forward to seeing you soon. Bye-bye.